Okay, what we see here is an incline with a weight sitting on it. This goes to one of the problems, that kind of a sort of capstone problem in the homework assignment. And everybody made some progress in this, okay? As I've said, it's the progress was let me do this again. Okay. There's too much of me in that picture. I didn't want to ruin it. Okay. The progress people made was largely due to getting wrong answers, and then it tells you what's wrong. And some people did 3 or 4 wrong answers. You still got substantial credit. Okay. I think maybe I'm giving too much credit for guessing, but maybe not. We'll see how it works out. I'm trying to sort of testing what you learned from that. And everybody's got a good picture. Okay. And this, this is like the roof, and this is like an air conditioner. What I just asked you to do was sketch a coordinate system and then sketch the components of the weight. Well, first of all, sketch this thing and sketch the weight vector. Then sketch a coordinate system and sketch the coordinates of that weight vector with respect to that coordinate system. Once you learn to do that, you're halfway there on all kinds of problems. Okay, it's a good start. Then you just got to do the arithmetic. You got to choose the right coordinate system. Now, the problem told you what coordinate system to choose. It didn't ask you what coordinate system you were going to use. It just told you use this coordinate system. And on a test, I wouldn't tell you what coordinate system to use. You'd have to know. Or if you're going to analyze something we're going to do in lab here today, you have to know what coordinate system gives you the simplest result. Any coordinate system will work. But if you don't choose just the right one, it's going to be pretty complicated. Choose the right coordinate system. It's very simple. Okay. So what we're testing is, first of all, do you know what coordinate system you want to use here? And I said, you can choose. I don't care what coordinate system you use right now. Any coordinate system is fine. Sketch the coordinate system, sketch the vector, and sketch its components with respect to that coordinate system. And then we'll talk about which coordinate system is the one that gives you the simplest results. Okay? Let's see if we're in focus. Am I blurry? No. Maybe I'm blurry in the real world, but that's compensating and the board's going to be blurry. I don't know. Everything's relative. Okay, well, so first we have a picture that looks like this. You got to be real artistic and draw a good air conditioner there. Okay, that's what air conditioners look like, because that's what that looks like. And that's obviously an air conditioner, right? Well, it kind of represents the air conditioner. So I didn't put it right at the top of the incline, because of course it's not right at the top of the incline. Although if you're sitting directly behind it, you might not be able to tell that. Okay. Well, we want to put it at the top of the incline, and that's okay, but then maybe your vector gets confused with this side of the picture, okay, with this leg of your triangle. So it's probably better to put it here. And the reasons that we'll get into in more detail than you want, you usually put a point at the center of whatever object is. Now, in that case, it's not totally appropriate to do that because we're not going to talk about the torque of this thing. That comes later. And obviously, if it was steep enough, this thing could tip over, right? I'll just mention tangentially, it's not important. So what we're doing right now, it's just another idea you can kind of store away is if this force vector was the way you draw it, if this is really the center of mass, what we call the center of mass. If the force vector, if the direction of the, okay, if a straight line through this point, parallel to the force vector, lies on the other side of this point here, it's going to tip. So if I had it a little steeper and put the point here, okay, you can see that the force vector would have a line of action that's outside of the object. That will cause it to tip. So that's kind of an intuitive idea that's I'm just kind of throwing out right now. I'm responsible for, get the neurons working on it. Now let's get to the point. The point was I asked you to draw a coordinate system. Okay. And many of you drew this coordinate system, most of you did. Here's X, here's Y. And then you drew your force vector in most cases. Okay, not everybody. Drew a force vector here. And that's not a good representation of this force vector. This force vector is straight down and this one at an angle. Okay. So we want to keep things consistent. We want down to still be down. So if you draw your coordinate system like this with this picture, then Y is straight up and down and X is this way. Okay. Now the picture that you get if you use a different coordinate system is going to look a lot like this, but the force is going to be straight down. Okay. So if we have the force here, this is not representative of the picture. Force should be vertical. Okay. Now, how are we going to make that happen? Well, if we just rotated this thing a little bit, that would be vertical, wouldn't it? And of course, that would rotate the X and the Y axis. Makes sense? So if I draw a coordinate system like this, then F can be vertical. Well, not sure what the angle is. We'll do some measurements and figure that out later. Okay. There's theta. Here's our force. Here's the x-axis that we want. Here's the y-axis that we want. Now, what's the angle between the force vector and, let's say, the nearest axis, which would be the negative y-axis? Maybe it's just looking at it at a weird angle. Okay. So I'm clear. I'm not blurry out here, am I? You're not seeing me as blurry. So, okay, the camera's good. Okay. Well, how far do I have to rotate this so that F becomes vertical? Well, if I rotate it so that the x-axis is parallel to the incline, okay, then F would become vertical. Assuming that you intend this thing to be at angle theta down here. So in the best choice of coordinate system, this would be rotated so that your angle theta is here. And the reason that's the easiest coordinate system to work with here is that that does rotate X up so that it's parallel to the incline. And that's what we want, because we want to look at forces parallel and perpendicular to the incline. So that now the forces that we're looking at, the X and Y components, one of those is going to be parallel to the incline, the other is going to be perpendicular to the incline. And now the coordinates are going to look like this. I'll go back to my good old orange chalk. Okay, I'll use a different color. Purple. Okay, so. This is FX, this is FY. When I was labeling this, I saw the X, and actually I just wrote an X because I wasn't. Okay. And you should then understand that your force is negative F sine theta I minus F cosine theta J. Not sure everybody got that. But both components are negative. This is in the negative Y direction, this is in the negative X direction. So if you're going to do it in terms of theta, there it is. Okay. Now, alternatively, there are times when you want to do this. This is kind of what I tell you to do when you've got the numbers. You can automatically get the quantities. And well, I said this is F1, just to help. Okay. F is, here's Fy, here's Fx. So I meant and intended to do this. Fy is negative F sine theta I of cos. I write these things out of habit. Well, this is Fx. Okay. Here's your Fx. Your Fy is negative F cosine theta J. So that F is Fx plus Fy. Okay. Now, the big reason we need to keep cell phones off is because sometimes if I pick up the rhythm, I start dancing. And if I start dancing, you're never going to want to look at dancing again. The image will be so traumatic. Okay? No, seriously, it's okay. And I wasn't tempted to dance anyway, so it was safe. Okay. Now, you might think I'm complicating things, and maybe I am, but But anyhow, I could write that as F times the cosine of 270 degrees minus theta times I, and F sine of 270 degrees minus theta times J, which means that I'd have been measuring theta counterclockwise from the positive x-axis. And then we could just automatically write down cosine and sine here, which I was wanting to do here, even though I know better. Okay. Okay, well, that's the vector, that's the mechanics of the vector thing. And it's all really straightforward. You just got to get used to it. Get your coordinate system in the right direction and write down vector components. Write down your vector and go from there.
130 is
Okay, well,
wait a minute, you still?
now having done that, we can easily answer the question of what's the component of the force perpendicular to the roof. Now, there are reasons we want the force perpendicular to the roof, not the force straight down, because the force perpendicular to the roof is the force that needs to be exerted by the roof to support this thing. Okay. Now, there's also force you need to keep it from sliding down. Okay. Fy is a force you need to support. Fx is, well, Fy is equal and opposite to the force. The force that resists Fy, the force equal and opposite to Fy, is the force that keeps the roof from caving in. Okay, well, the force the roof has to exert, provided this thing doesn't weigh so much that it caves the roof in. Okay. So right now, this thing, you can look at it. I'm not going to rotate the camera. This thing's sitting here. In the real world, you saw it. Okay, on video, and you can see it if you're sitting here and laugh. You notice that that wood block isn't caving in. Well, that wood block will probably hold up a rhinoceros. Okay. And that isn't nearly strong enough to cause the wood to bend above. Okay. Like the break. Okay. You also notice that the mass isn't sliding down the incline. Now, if the incline gets steeper, it will slide down because its friction is keeping it from sliding down. Now, if it's an air conditioner, you bolt the thing down to the roof. And resisting this force, which is parallel to your roof joists, isn't going to challenge your roof at all. Okay, this force wants to bend your roof joints, so you don't want too much. If this force isn't enough to bend the roof joists, then this force isn't enough to compress the roof joists. It's really hard to compress wood. Okay, typical roof joist could hold 10 tons if it doesn't bend and buckle. And that's more than you really need to know, because I think we're taking statics, so that's what's kind of thinking about. Okay. So this is a representation of everything we need to know. Just a mathematical representation. It's a picture. And it tells you everything you need to know to solve this entire problem. Now, your assignment gives you step by step, tells you how to break it down and so forth. That's good. But you need to be able to do that without being prompted a dozen times. So when you do these problems, you need to learn them, learn what you're doing well enough that you can do them independent. You can do a similar problem independently. So I could come in here with a quiz on this thing. Okay. And I say that I don't think the results would have been great. Because first place, I think that the software is giving you too much help. So you got to be aware of that. You got to be aware, you got to be able to do this without all the help. The goal is not just to answer the half dozen or more leading questions they ask you. It's to incorporate that process and be able to apply it to other problems. Now, I can draw a little more in there. Okay, so this is the force. Exerted by gravity. And then while we're at it, we want to see the force. The forces that have to be exerted by the roof. And those forces have to be sufficient to balance these forces. They have to be equal and opposite. Okay, so what you're going to need is you're going to need a force over here. And a force here. Where this is equal and opposite to this, and this is equal and opposite to this. Okay, so let's call this force I don't like to use E because we use that for electric fields. We're not going to see those for a while. So that probably have to mess up here. I'm going to use E for equilibrium. Okay, because these forces need to be in equilibrium. Otherwise, this thing is going to be moving relative to the roof. So if you consider the roof to be stationary, this thing needs to be stationary, obviously. You want that air conditioner not to move relative to your roof. Okay. Now your roof is moving because the earth is spinning and we're going around the sun and the galaxy is moving and all kinds of things are going on. Okay. But locally, we just think of the roof as being stationary. At least it's not accelerating. It actually kind of is with very small acceleration relative to the rest of the universe. Okay. So the equilibrium force, EX, EY, equals what? EX. So can you write out what those forces would be? So that E equals what? What's EX have to be? What's EY have to be? And what's E have to be? Okay, so people have it. And make sure when you draw your projection lines, you're really drawing projection lines. Go to a right angle, the tip of the vector over to the axis that you're projecting on. So your EY is going to be, a lot of people said, well, it's negative FY. Not necessary to write it that way, but you can see that it's got to be why am I writing cosine assumption? That's a theta here that y'all can stuck on me. It's F cosine theta times the I vector times the J vector. Automatically want to write I with cosine. EX is negative F X equals F sine theta times I. So the E, I didn't leave myself room to write out what E is. No room to the right, not enough room to the right, not enough room below, but here we go. E equals dxi. I'm just going to write it this way. Dx vector component dx plus the vector component dy, which equals write things down automatically again, which equals Sine theta I plus F cosine theta J. Okay, so now I've got a conceptual idea of the force component perpendicular to the incline and the equal and opposite force up here. And force component of F parallel to the incline and equal and opposite. So now I have the equilibrium force, which is, I'm not going to draw it up here, I could. There's a good reason. And we can then answer the question. I'll write it this way. It's F cosine theta the more intuitive idea. I'm going to say inward because it's in this direction, that's in toward the house, right? And F prime theta down the state. And you can see that directly from this picture from the F to the FY. If you have the axes in the right, in the, can't say right or wrong direction, this can be worked out in any coordinate system, but in the most convenient coordinate system. It's most convenient because the components, the force components that you want are parallel to the axis. If your picture was like, well, we don't want it to be like this. If you wanted to use axes like this, then your F would be straight out. Okay. But the components of this vector are just negative F and the J direction, negative F, that's just negative Fj, right? And what we would then have to do is I have to say, okay, let's find the components of this force in the direction perpendicular to the roof. Okay, and let's find the components parallel to the roof. Well, you'd end up with the same picture. Components perpendicular to the roof are these, no matter what your coordinate system is. Your components parallel and perpendicular to the roof would be here and here, and you're back to that picture. So there's really no point in drawing this picture. Because you're going to have to then, if you do it with relative to these coordinate axes, you're going to have a vector in this direction to project this onto using a scalar product. Okay? You could do that. We'd have to figure out what this vector is and what this vector is. And you just get a lot messier and conceptually not as easy to see. This is conceptually easy to see from the very beginning. Your components are the things you're looking for. So take a lesson on that, but mainly ask yourself, after doing this problem, did you really learn what to do? Or did you just answer a bunch of isolated questions until you got the right answer? Okay. And if you did, that's okay, you got the right answer. Then you need to go back and put it together. you need to work on it until you can complete the analysis in one way or another. Now, my analysis is dependent on this picture and on these vectors represented the way I've chosen to represent them. Book's analysis said, oh, here's your target variable, dot, 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 here's your formula, so forth, okay? Either approach is okay. Both approaches work better. It's like having binocular vision instead of monocular vision. But one is going to appeal to you more than the other. So you follow that one, think about the other. And bottom line is think about the picture. Get the picture, because the picture tells you more. For most people, the picture tells you more than the formulas. Formulas are a way of getting it without understanding it. Pictures then show you what you just did and lead to understanding. Okay. So hopefully you take that to heart. And everybody's got a different learning style, different mix of how you use pictures and how you use formulas and so forth. So find your own path and make the best of it. Again, try to understand it both ways. Okay, just another thing that's come up in discussing. We're discussing the velocity of the ball as it goes off the edge of the ramp. We've discussed the fact that using the techniques of uniformly accelerated motion, which theoretically you already know, because you know the premises, okay? But working out the details, the devil's in the details, and there's plenty of devil in this one, okay? And it's kind of a difficult analysis. If we roll a ball down an incline and then measure, first of all, the angle of the incline, and then how far the ball goes and how far it drops, how far it goes in this direction, how far it goes in this direction before it hits the floor, we can conclude what the x velocity is and the y velocity. So then the question was, well, then how fast does it move? And a little uncertainty in that. Some people said, yeah, I'm figuring through. Some people are still thinking about it. It's natural at this point. But here's the picture that goes with it. Here's a Bx, here's a By. Okay. And I just drew this picture without the anything in orange. Just drew this picture and said, can you draw the result? Okay. Now, if you had to think about that, well, get used to it so you don't have to think about it. If you have two perpendicular vectors, we have any two vectors, okay? Basic principle is if you got a vector here and a vector here, it's not a right angle. We can draw the parallels and then here's the result, right? That's the graphical picture of the vector. So given this and this, it should be automatic. Well, okay, make a parallelogram out of this, which is a rectangle in this case. The x and dy would be parallel, perpendicular. Then it's very easy to calculate the magnitude of the vector using the Pythagorean theorem, vx squared plus vy squared, square root. Okay, or the dot product, which is equivalent. Sometimes that's convenient. And you want to understand why the dot product gives you vx squared plus vy squared. And then you take the square root of that. Okay. So you want to really kind of lock these basically, it's basically high school trigonometry. But you want to really lock it in. Because if you stumble over it, you're getting your way to try to solve problems. It's going to take you longer to solve them. You save a lot of time in the long run by just nailing these things right now. Okay. And some you got to nail better than others. Some you're taking statics, you got an automatic advantage. Okay. But in statics, a lot of stuff's just done by formulas. Okay, but you got pictures. I mean, pictures are really important. So this will also help you with your statics. You want certain things to just be automatic. In this course, we don't use law of cosines much. Statics, you got to use it. Have you already used it? Yeah. Comes up because it's shorter. You do it all the components sometimes. And it's also visually intuitive. There's a couple places in second semester where it comes up. But that's again, law cosines is 11th grade trigonometry. Okay. So expect you to have it when you need it. And I think you will. Okay. Now we're talking about what happens if a ball rolls down an incline. And we've got a setup, and I'm not going to bother. Okay, here's the ball, here's the incline. And it's a flat foot under. Well, I'm just going to manipulate it. Okay, so here we go. There's the ball. Okay. Well, we can look at the force. The force of gravity is acting downward. We set up an x-axis parallel to the incline, a y-axis perpendicular to that, and we see that the force is going to be a little ways out from the y-axis, one direction or another. Now, the way I've got it here, the force would be, well, the rotation would be like this. The x-axis would be going down. The force is straight down, so it'd be in the fourth quadrant. Okay. And if you want to look at it the same way this way, you can do that block and forward. If you do it this way, then you have something very similar to this. Much smaller angle, so this force is going to be much closer. Well, the force is still going to be vertical, but the rotation, you're going to have the coordinate axis rotated from the vertical horizontal by less. So that this angle is going to be smaller. If I increase the slope, or you see it gets going a lot faster, meaning it has more acceleration. And theta gets bigger. The bigger theta gets, the bigger x gets, because the closer theta is to the y-axis, the closer your projection is going to be to the origin of your less distance along the x-axis. So you really want to make sure you understand that intuitively, so you understand what's going on with this experiment, in which we're going to gradually increase the steepness of the incline. Okay. And then see how far the ball goes after it goes off the edge. Does that make sense? Okay. Good. Another thing we need to do in this experiment, and I'll get to that, we need, well, that's a detail. We're not going to do that on video. Okay, we had a great lab session. People got really good data. They were careful about it. They have inventive ways of observing things. They were proactive. Yeah, so y'all did a great job. So we want to get this data reported. And I want a data report by Monday. And over the next week, spreading it out a bit over the week, we want to get a good written report of the labs so that people can then read what other people have done during the following week in preparation for the next set of labs. I'll give you more details on that. And there'll be a few calculations that I'll want Sunday along with your raw data. Remember, raw data is just what you see, no calculations involved. Okay, even if you're on a meter stick. Okay, if you're measuring something on a meter stick, if you measure 20 centimeters to 80 centimeters, you don't call that 60 centimeters. You call that a measurement from 20 centimeters to 80 centimeters. You do the arithmetic later. Now, obviously, everybody can figure out that that's, what is that, 77? That's 60 centimeters. Okay, everybody knows that. Can do that quickly, but if it's 21.8 centimeters and 73.2 centimeters, you don't want to do that calculation in your head, and you don't want to take time to punch it into a calculator. So sometimes you want to do kind of a cursory calculation, but you're not going to report that. So the raw data, and then do the calculations based on raw data. The time interval between these two blips on Audacity output is not 0.637 seconds. It's from this many seconds to this many seconds. And of course, that's the way everybody recorded. So there's a raw data, and then there's the process data, if you wish, where everybody is going to figure out the two time intervals to see if the ball takes longer going up or coming down. I think we get a pretty clear result. But I want to see what everybody got, because there are other things that we can determine from that. For example, we get an indication of whether each person tends to click for the event of the ball stopping a little bit early or a little bit late, and everybody has a tendency. So we want to start getting a handle on how you measure the tendency of everybody to measure a little bit on this side or a little bit on that side. Okay, well, more about that, and we'll do some cursory. I'll do some cursory results when I assemble everybody's data, for example, on the experiment where we use Audacity. We also want to see how consistent the results were rolling the ball down the ramp and off the edge with different slopes, different dominoes. The thicknesses of the dominoes vary, which is why I had you mark the dominoes in the order they were used, so that we can go back and actually measure the thickness of the dominoes and see if it has an effect on the overall results. We'll see more about that later on. So for right now, I want the data report by Sunday. Most people probably aren't going to watch this video, but here it is for reference, and I'll put it in writing and get it to you, by the end of the day. Okay, so that's what we're into. We're into measuring consistency. We're into observing consistency. We're into observing differences in the way different people observe things. And we're also into what are the clever things you did that nobody else thought of? Or how did some people do it when other people did it a little bit different? People had different ideas about how to do things. And that's exactly what we want to see. We want to see what the ideas are. We want to see what the effect of those ideas is. Whether it's just a good idea or is this a better idea? How do we adapt in our own observational process as a result of what we see other people do? Okay, we don't imitate other people, we evaluate what they do. So is that a good idea? Is that a bad idea? Maybe we need to try it and see. Okay, well, that's where we are. Over the next 2 weeks, we'll get enough knowledge of how to analyze uniformly accelerated motion to do a complete analysis on these experiments. And then in our next lab session, we'll apply some. Okay, well, very good.